Viaggio nella segreteria, mettere 4 cose in una valigia. Compro cartoline ma non le spedisco quasi mai. Le scrivo e le riscrivo e butto via. Poi vado a fare il check-in, adoro partire, amo le hostess, amo il duty free. Check-in, mi piace guardare la mia borsa all'aeroporto a raggi X. Voglio fare un po' la misteriosa nella parte della straniera, navigare i 7 mari su una nave da crociera. Un certo mi inviteranno a cena al tavolo del capitano e passerò le sere ballando il valzer. 1, 2, 3.
Good afternoon. So this is the sixth and the last plenary lecture of this conference. And I have the pleasure this afternoon to welcome Guillaume Haïat from France. Guillaume is a senior research director at the CNRS and an adjunct professor in the ETS in Montreal. He graduated from École Polytechnique in France in 1998 in physical acoustics. He defended his PhD at the French Atomic Energy Commission in 2004 in the domain of ultrasound non-destructive evaluation in the nuclear industry. Since 2004, he has been working in the domain of bone quantitative ultrasound and biomechanics, and he is an associate editor in the Journal of Acoustical Society of America, Medical Engineering and Physics, Ultrasound in Medicine and Biology, and Journal of Mechanics in Medicine and Biology. He is the PI of the BONE-IMPLANT project funded by the European Research Council, and that focuses on the biomechanical determinants of the osseointegration phenomena. So please, Guillaume.
Thank you very much, Frank, and I would like to thank all the organizers for giving me this great honor to present the work of our group in Paris. It's really an honor for me, so thank you. So in this talk, I would like to convince you that studying the bone implant the bone implant interface is not only of interest from a medical point of view, but it's also of great interest for an acoustician. So you will not need any knowledge in biology or biomedical fields, but even if you don't have any knowledge in this field, you probably know that endoseous implants are widely used in the clinic. Probably some of you have such implant in your body right now. They are used in different fields of surgery. In orthopedic surgery, the aim here is to restore the functionality of joints, such as the knee or the hip. Also in maxillofacial surgery, you see the kind of application that are employed. And eventually in dental surgery, dental implants being the most currently used implants. So there remain important risk of failure, of surgical failure, which may have dramatic consequences, and that's a really important public health issue. The surgical success depends on the evolution of the biomechanical properties of the bone implant interface. And so the way the surgeon do to realize the surgery is always pretty much the same. They first drill a hole that has a slightly smaller diameter than the implant size, and then they put the implant in place in the bone tissue just by screwing it into the bone or by impacting the implants so that it stays in place due to the pre-stressed state of the bone. So that's called the primary stability, the stability of the implant just after surgery. And in this case, they need to find a compromise between a good stability that prevent micromotion at the bone implant interface that are detrimental to the evolution of the biomechanical state of the interface. But you don't want to have a too important stability either, because it can also lead to bone necrosis. So they need to find a compromise. And after that, after the implant is placed into the bone tissue, several weeks or several months after surgery, bone will start remodeling in order to adapt its structure to the presence of this biomaterial. And this is done through remodeling phenomena around the implant surface. That's called osseointegration phenomena. So basically, bone will grow around the implant surface, and that will lead to the secondary stability that is determinant for the eventual, for the outcome of the surgery. So these osseointegration phenomena are really interesting because they depend on many factors that you see here. They first depend on the implant manufacturer. So the implant properties in terms of geometry, in terms of surface roughness, surface treatment, maybe biochemical treatment, etc. The second thing, of course, is the surgeon. How do they work in terms of protocol, in terms of aseptic condition, of loading protocol, and in this case, the surgeon used a non-standardized technique. So there is a really high dispersion of the techniques and of the protocol that are used in the clinic. And of course, the patient. The patient is very important. The bone quality, the behavior, the health status of the patient. So everything matters. There's been quite a lot of work done in the literature on the characterization of the bulk of the bone in the bulk. However, the works focusing on this interface is relatively rare, and you see an example of this interface here. That's an histological section. So the implant is here. The pink is the bone. This is newly formed bone tissue, mature bone tissue, and you see a schematical representation of this interface. Actually, it's an interface. You see the implant, and here you have a region around 200 micrometers. That's really the scale we are looking at, where you have newly formed bone tissue that remodels in relation to osseointegration phenomena. And so that's really, the aim is really to be able to characterize what's going on in this region in terms of structure and of biomechanical properties. So that's a complex problem, first because bone is really an exciting medium from an acoustical point of view. It's viscoelastic, heterogeneous, it's a composite material, anisotropic, nonlinear, so it has all the properties that you like to see for a material. Moreover, it evolves as a function of time because it adapts its structure to the mechanical stresses it undergoes. And eventually, the presence of a rough interface, the roughness of the implant, the microscopic roughness is of the order of 5 micrometers. So that's an order of magnitude, but you also have the shredding that can be of the order of several millimeters. So that's an exciting problem, and much of the work that has been done in this area were led by medical doctors or implant company, and they often used empirical approaches. So there is really a need for engineers to tackle this problem in order to bring quantification into a field where mostly empirical methods have been developed. So in order to tackle this problem, you need to work in an integrative manner by coupling multiscale modeling, multi-physics experimental approach, and experimental surgery. So why multiscale modeling is because the main reason is that you don't build bone. In the industry, you build all the material, but here you don't build bone. It's built by itself. So that is difficult to control all the parameters. And the only way to control the influence of each parameter is to do multiscale modeling in order to understand what's going on at all the scales. multi-modality experimental approach is needed to retrieve as much information as needed at different scale, and experimental surgery, you can't go without it. We need the surgeon for that. It can be animal experiments, experiments in cadaver, or even in patients in clinical trials. Okay, so that's the outline of what I will present you today after this short introduction of the problem. I will describe some destructive methods. So obviously, that's animal study that aim at understanding the phenomena. And then I will try to describe some non-destructive methods that we've been developing in the lab on dental implant and also on hip implants. Okay, so first, destructive method. So in this case, again, the aim is to understand how we can characterize this interface using acoustics in order to really focus on what's going on around, let's say, 200 micrometers around the interface. And eventually, we would like to use that to implant, that's a long-term goal, to improve the performances of the implants. So that's the multi-modality experiments that we have used or can use. Except the first line, because X-ray and MRI that are widely used imaging technique in the medical fields can actually not be employed for implants just because of diffraction phenomena, because implants are usually made of metal, and so you have diffraction and artifacts, so you cannot see what's going on 200 micrometers around the interface. So these techniques cannot be used, but we can use all the other techniques that I'm going to detail here. Histomorphometry is just you look with a microscope at the interface, very simple, but that's still the gold standard. And you can use these other techniques that I will detail in a moment. Okay, so remember I told you about experimental surgery. So that's very important if you want to use to study this kind of material. And the problem is that if you use real implants that are actually employed in the clinic, they have very complex shape that will generate complex stress fields. So it's very difficult to work in a standardized situation. So therefore, we have developed our own animal model. So it's called a surgical model or animal model. It's in rabbit. And you see an image here. So that's the rabbit femur with the axis of the femur right here. And it's very simple. It's a cylinder, 5 millimeter diameter, 2 millimeter high, made of titanium alloy, which is the classical metal that is used for implants. And you see the implants is maintained using an elastic string so that it stays in place on top of the bone. So basically, around the implants, you have PTFE, that's the white part that you see here, and you see a cross-sectional view of the implants, of the cylinder. Again, 5 millimeter here, 2 millimeter here, and the PTFE cap that aims at avoiding bone attachment around the implant. So we are really studying on what's going on underneath the implant in this region. The surgeon made also irrigation hole underneath the implant to allow for free circulation. There are two advantages of this implant model. The first one is that you have a planar bone implant interface. So you see the planar bone implant interface here. Of course, it's rough, you have roughness, but the macroscopic geometry is planar, so that we can work in standardized situation on control, as much standardized as possible, in controlled situation. So that's the first advantage. The second advantage is due to the fact that you see here you have a PTFE layer that goes underneath the implant, so that here in this region you have what we call a bone chamber. So that's a region where initially there is no bone, okay? And then the bone will grow in this chamber, so that we are certain to be able to distinguish. Here this region is 200 micrometer high, and so we are sure to be able to distinguish newly formed bone tissue and mature bone tissue. And so we use this, this possibility to distinguish newly formed bone tissue around the implant with mature bone tissue in order to determine the biomechanical properties. And for that, we used nanoindentation that allows to retrieve mechanical properties at the scale of several micrometers. So we did some nanoindentation measurement in this region corresponding to mature bone tissue, and in this region corresponding to newly formed bone tissue, and we compared the two in order to see, to study the evolution of the biomechanical properties of newly formed bone tissue around an implant. So that's the results that we have obtained. You see here, the orange is the indentation modulus, the pink is the hardness, for a sample with 4 weeks, 7 weeks, and 13 weeks of healing time, and here for mature bone tissue. And basically, and the results are significant, you have an increase of the biomechanical properties of newly formed bone tissue as a function of healing time. And that's probably due to an increase of the degree of mineralization of bone tissue. Okay, so based on this result, we also applied another technique in conjunction with a nanoindentation, which has the advantage of working at the same scale. And so that's a micro-Brillouin measurement. So basically, it's a measurement of the acoustical velocity at around the gigahertz. That was done in collaboration with Doshisha University in Japan. And basically, we did the same. So we measured the ultrasonic velocity again in 1 micrometer, several micrometer, size of several micrometer in newly formed bone tissue and in mature bone tissue. So that's the results here. And again, we saw that there was a significantly lower velocity for newly formed bone tissue compared to mature bone tissue. Okay, so basically that results allowed us to understand the evolution of the biomechanical properties of newly formed bone tissue. But this surgical model has also other advantages, and we also wanted to assess what's going on in terms of fracture. So for that, we did some fracture experiments, and that's if we want to do fracture experiments on a sample like this, the first idea that we had is to pull out the sample like that. But if you pull out the sample like that, the problem is that the crack will initiate here, here, but then it will propagate very quickly so that you can't actually retrieve some useful or some meaningful information on the effective adhesion energy or the stress intensity factor. So we had to go to another strategy, and what we used here is described in this figure. Basically, we attach to the top of the implant a torque sensor, and then a rotation stage to the bone, and then we rotate. And see, if you rotate like that, what happens is that you're going to initiate a crack in this region, here, in the outer part of the bone, that will propagate inside the implant in a steady state manner. So that's very important, because doing that, you can propagate a crack in a steady state manner and then retrieve some meaningful information, in this case, on the stress intensity factor. So that's what we did. This is called a mode 3 crack propagation. It is not only adapted to the animal model, but it also occurs in real clinical implants. So it's not only for the experiments, but it has a physiological meaning. And again, it's a stable mechanical testing. So I'm not going to go into the details, but just to tell you that we've developed analytical model coupling friction and adhesion. So that's called Dugdale model, in order to understand crack propagation and what's going on. And we were able to fit and to use the results of this model in order to derive here what you see, the mode 3 fracture energy or the stress intensity factor for different samples. And you see the order of magnitude that we have obtained. Okay, so just to summarize, we measured the biomechanical properties of newly formed bone tissue. Then we characterized the behavior of the interface in terms of adhesion. And the last set of experiments that we did was to use ultrasound to try to characterize this interface. So since we have the most simple configuration that we could think about was to, after sacrifice of the animals, of course, to immerse the sample that you see here. So that's the bone, that's the implant right here. So we immersed it in a tank, and then we used a very simple focused transducer, 15 megahertz. And so we made sure that the axis of the transducer is perpendicular to the implant surface. And then we had a displacement of the sample in order to have a scan of the surface. And the transducer was working in a very simple echographic mode, so that you have an echo. And the echo that you get in this kind of system is quite simple. The first echo is the echo of the water implant, okay? Then the wave propagates inside the titanium, and then you have an echo of the implant bone interface, and that's the implant bone interface that we are interested in. Okay, so that's the typical results that we have obtained. You see the first echo, the echo of the water implant interface. So that's a broadband ultrasonic pulse, 15 megahertz. And that's the second echo that you see later. That's the echo of the implant bone interface. The black line corresponds to a sample obtained after 13 weeks of healing time. And the gray line corresponds to a sample obtained after 7 weeks of healing time. And what you see here is that if you look at the water implant interface, well, you get exactly the same results. That's totally normal because nothing happens there. It's just only water implants. But when you look at the implant bone interface, then you see on this example, but again, it is significant. We did it on many different samples, that you have a decrease of the amplitude of the echo when you have an increase of healing time. So the echo obtained after 13 weeks is lower than after 7 weeks. Okay, so that was significant. Here, that's an example, and we wanted to try to understand why is that. So to do so, we did what surgeons do with animal study. They cut the implant, and they look with a microscope at the interface to see what's going on at this interface and to try to determine what they call a bone-implant contact ratio, which corresponds to the amount of bone in intimate contact with the implant. So that's called histological analysis. It's widely used in the implant field. And when you see a zoom, you see the scale here. That's what you get. So the black is implant. The pink is bone. And the white is soft tissue. It's non-mineralized tissue. It's actually kind of very soft tissue, so it's like liquid at the interface. And what we saw, and this is well known, is that the bone-implant contact ratio is lower for 7 weeks than for 13 weeks. That's the result that you obtained. And this is not a surprise, because with healing time, you have more and more bone in contact with the implant. That was logical. But when we looked at these images, we say, okay, then in this case, we have a lot of, let's say, liquid, something like close to water in contact with the implant. Here we have bone. And as you know, the reflection coefficient, that's basically what we measure, is given by the gap of acoustical impedance. And in the case where you have a liquid, well, the gap of acoustical impedance is much higher in this case than when you have bone, mineralized bone tissue, where the velocity as well as the density is much higher than in a liquid or in water. So we have here a empirical explanation on what's going on and on why we have a lower amplitude of the echo for 13 weeks of healing time compared to 7 weeks of healing time. However, this is only a phenomenological expectation, so we wanted to go further and do some simulation in order to understand what's going on. So this simulation was done using 2D time domain finite element modeling. We used the COMSOL in this case, and basically we measure the roughness, the 2D roughness of different samples, and we used it as input data in the model. Here we impose the pressure on one top of the geometrical configuration. So here we have the implant. Here you have bone tissue. You have the rough surface that is extracted from surface profile measurements. And in the interface, again, it's an interface, we considered a layer of liquid or soft tissue. It's like water. It has the behavior of water, basically. And in this region, you see that we have water, and we have a parameter here that determines basically the thickness of the water layer. So when W is equal to 0, it means you have a fully osseointegrated surface. And when it's very high, it means you have no osseointegration. So the parameters that we have considered here was the roughness, the soft tissue thickness, and of course, here the frequency was 10 megahertz, but we also could vary it. We assumed homogeneous isotropic material and no absorption in the computation. So that's the kind of results that we get. You see the video. You see here, you will see the video of the wave propagating in the implant, then interacting with the bone implant interface. You see the liquid layer, and then coming back up to the top of the implants. And basically, we considered a planar receiver on the top of the implant here in order to record what's coming back from the implant. That's here, from a more quantitative point of view, you see here the signal that you get. The dotted line is the envelope. So this is the input signal. And this is the reflected signal. And the output of the computation was very simple. It was the reflection coefficient, so the ratio of the amplitude of the envelope of the reflected wave divided by the incident wave. And we could play with different parameters, and the most important parameters to play with was the water thickness, because it really corresponds to osseointegration. You see that for W equal to 0, it means, again, fully osseointegrated surface. When you increase W, you will increase the reflection coefficient. And this is completely in line and quantitatively comparable with the experimental measurements. And after a certain time, you have a plateau. And for very high water thickness, you have a constant value for the reflection coefficient. And one nice thing here is that the value that you obtained here for W equal to 0 is the same reflection coefficient as a planar bone implant interface. And in this case here, it's the same value of the reflection coefficient of a planar implant water, implant liquid interface. Okay, so we were quite happy with that result. We quite corresponded well to the experiments. And we used this in order to understand what's going on for when there was an interaction between this bone implant interface and an ultrasonic wave. And remember what I said at the beginning, the overall aim is to develop, of course, non-destructive method that could maybe one day be useful to surgeons and, of course, to patients. And we use this knowledge in a very controlled configuration to develop a method. And I'm going to describe this method aiming at measuring dental implant stability. Okay, so what is a dental implant? It's very simple. It's a screw. And the surgeon, to do the implant surgery, they make a hole in the bone, okay, at the initial surgical phase. They make a hole, and then they put the implant. It's a screw, very simple. And then they wait a certain amount of time, between 0 and 1 year. They don't know exactly. It's a really empirical approach. Before they do the loading, so they put the prosthesis, they put the teeth here. And this amount of time between initial surgery and loading, implant loading, is very important because they need to make a compromise between a long time in order to allow for bone remodeling around the interface, but it should not be too short because otherwise the interface may be damaged. So they need to trigger this in a patient-specific manner, and it is still very difficult to do so, and it really depends on the proprioception of the empirical approach of the surgeon. Okay, so, and of course the patient would like to decrease this time because the patient do not like to have a hole in the mouth. Okay, so we developed a very simple method, ultrasound method, that is described here. So you see the dental implant, and basically it's a 10 megahertz transducer. You see here the diameter is around 5 millimeter. The transducer is a planar monoelement transducer. And then on top of the implant, you have a screw. And so you can screw this transducer into the implant. Okay, so very simple. You see the configuration here. So this device, we screw the transducer into the implant, send 10 megahertz, send a broadband ultrasonic pulse. Then the ultrasound wave will propagate in the implant. And this transducer works in an echographic mode, so you record what comes back, whatever comes back from the implant, and you see the kind of the signal that we get. It's a coda, okay? It takes a long time. And then we can treat the signal. And what happens is that when you have a very stable implant, it means you have a lot of bone around the implant. So the reflection coefficient is quite low, as we showed before. So the energy can basically go out of the implant, and so you get less energy coming back from the implant than when you have an unstable implant, where you have a lot of soft tissue, of liquid around the implants. So the gap of acoustical impedance is high, and so the energy kind of gets trapped into the implants, so that you get a lot of energy coming back from the implants. So basically, based on the amplitude of the echo, we could derive a very simple indicator, because surgeons need very simple information. So an indicator, a number, based on this amplitude. Okay, so that's called the ultrasonic indicator. And that's basically the amplitude of what's going back in terms of acoustical energy from the implant. Okay, so that's what we did, and we wanted to validate this method. The problem is, how do we validate? What surgeons do in practice, in order to assess the stability of the implant, that is important to help them derive their surgical protocol, they take a metallic rod, they hit the implant, listen to the noise, and based on what they hear, they kind of decide what they should do. Of course, we cannot use that. As I mentioned, X-ray cannot be used, because you don't see the interface. So it's not used for implant stability measurements. There is a device on the market that's called Hostel, and it's quite simple also. You screw a metallic rod into the implant, and then there is a system using electromagnetic wave to excite the first bending mode of the metallic rod. And based on the resonance frequency of this first bending mode, the system makes a measurement and gives a score. That's called the ISQ. And this gives an indication of the rigidity of the bone implant system. The higher the rigidity, the higher the resonance frequency, the higher the ISQ. And so the aim of this study was to compare this resonance frequency analysis with our ultrasound method. Okay, so we did that, and in order to work in standardized situation, we considered an in vitro study. So using bone blocks, it's actually bone phantom that are widely used in the bone field, is polyurethane foam, different kinds, different density. And we consider only one type of implant. And we considered various kind of configuration by varying the type of test block, the diameter of the hole, the insertion depth of the implant. And for each configuration, we made a face-to-face comparison between the resonance frequency analysis and the ultrasound response. And of course, at each time, we record the value of the ISQ in the resonance frequency and the ultrasonic indicator in the case of ultrasound. We compare the value, but we also compare the standard deviation, the reproducibility of the measurements. That's the parameter that we tested that are all related to implant stability. We tested a variation of trabecular bone density. When you have an increase of trabecular bone density, it means more stable implant. All other parameters staying the same. We tested a variation of cortical bone thickness, so that's the layer of cortical bone. When it's higher, when the cortical bone thickness is high, it means a more stable implant. We tested the effect of the diameter of the hole. When the diameter is bigger, the implant is less stable. And the implant insertion depth. So again, when the implant is inserted more deeply into the bone, it is more stable. And for each time, again, measure the ISQ, measure the ultrasonic indicator. Okay, so that's the results. You see here in this figure the variation of trabecular density. So here it's more stable implant, more dense trabecular bone. And the red here is the ultrasonic indicator. It decreases when the implant is more stable because you have less acoustic energy coming back of the implant. It is normal, it is logical. And here, the circles that you see here is the ISQ. It also increases as a function of when trabecular density increases because the bone implant system is more rigid. So again, it is logical. So we were quite happy with that, but we said, okay, how can we compare? And to compare, very simple way is to say, okay, to determine the error that you make on the estimation on the trabecular density using these two methods. And to determine, to have an estimation on the error, we we used two things. The reproducibility of the measurements. And you see the reproducibility of measurements using ultrasound is much lower than using ISQ, the resonance frequency analysis. And also the slope, this slope, and this slope. And by combining the two, we can derive an error on the estimation of the trabecular density using ultrasonic indicator and using the ISQ. And you see that the error is smaller when you use ultrasound. Same thing when regarding to cortical thickness variation. Here is 1 millimeter cortical thickness, 2 millimeter cortical thickness. The implant is more stable here, so it's normal. You have a decrease of the ultrasonic amplitude coming back from the implant. And in the case of the resonance frequency analysis, you have a small increase. Standard deviation were not great in this case. And again, we could compare and show that we can retrieve with more precision the cortical thickness using ultrasound than using ISQ. Last set of experiments. Here, a variation of the final drill diameter. Again, the red is when you increase the final drill diameter, implant is less stable. You have an increase of the ultrasonic indicator. That's normal. But when you see the results with the resonance frequency analysis, you see here that you get pretty much the same results for low drill diameter and for high drill diameter. So you cannot really compare all the situations. And eventually, for when you screw an implant, so when you go from here with ultrasound to here, you screw the implant, you increase the stability, so you decrease the ultrasonic indicator. That's logical. And then when you unscrew it, you go in the other direction. You increase the ultrasonic indicator. That's logical. You get pretty much the same results for the resonance frequency analysis. And again, we could derive an error on the estimation of the insertion depth that is lower using ultrasound than ISQ. And these results are consistent because when you use ultrasound, and we could show that with using numerical simulation, you are looking at what's going on, let's say around 30 micrometer around the interface. Whereas when you use a resonance frequency analysis, the vibration goes all over the test block or all over the bone. So you're not testing only the interface, you're testing the entire configuration, and that's why you have less sensitivity. Again, we need to develop finite element modeling, so that's what we did, again, using COMSOL. In this case, we considered a fully bonded interface, and we used the 2D finite element, 2D axisymmetric finite element analysis. Again, you see the imposed pressure. This is the dental implant, and the medium around corresponds to soft tissue or to bone according to the situation. The simulation was done at 10 megahertz. You see an image of the wave propagating in the implant, and you can see that it's actually a guided wave, and we have shown that in another study. You see the implant is here, and you see the surrounding tissue is here, and here you have PML. Okay, and more this is qualitative, more quantitatively. You see here a comparison between experiments and simulation in terms of the ultrasonic indicator. So the dashed line is numerical results when you unscrew an implant, and the solid line is the experimental results when you unscrew an implant in a similar configuration. So you see that you have pretty much a good agreement between the simulation and the experiment in this case. Of course, we need to do in vivo study in order to compare the quantitative ultrasound and the resonance frequency analysis, and that's what we did. So we asked the surgeon what should we do, and they said, okay, use sheep iliac crest, okay, and so they did it. They put the implant into the sheep iliac crest, as you see here. So the implants are here. This is the sheep iliac crest. And we used always the same dental implant, measure the ISQ, measure the ultrasonic indicator for different healing time, except that we modify the ultrasonic indicator just to have an increase of the ultrasonic indicator when the implant is more stable, because it seemed more logical to the surgeon. We consider different healing time, 0 and 7 weeks for one given set of implants, and 0, 5, and 15 weeks for another set of implants. I'm not going to show you all the results. You can see this publication for more details, but just to give you an example of the results that you can have. Let's look at the green curves. And the solid green curve is a comparison of the ultrasonic indicator at 0 time of just during the insertion, during surgery. And here, at 7 weeks of healing time, you have an increase of the modified ultrasonic indicator because you have osseointegration, so that's normal, okay? If you look at the results using the resonant frequency analysis, you see that if you make a measurement in one direction, you have an increase, but in another direction, you have a decrease. And that's because when you do the measurements, you are using this non-contact excitation, and the results depend on the orientation, basically. So in this case, the results were not consistent. But when you look at the result for another implant, where you have 0, 5, and 15 weeks of healing time, the ultrasound is given, the results obtained with ultrasound is given with a solid red line. And you see that between 0 and 5 weeks, you have an increase of the ultrasonic indicator because you have osseointegration. That's normal. And after that, you have a plateau, and that's also normal because after a certain time, these implants are not loaded, so the osseointegration phenomena are not stimulated, and so after a certain time, it just stops. However, if you use Hostel, you see that you have kind of the similar results, but with a lower reproducibility or lower slope, and you see the comparison again here in terms of the error on the estimation of the implant. So we did many different, I think 82 implants or something like that, but that's just an example. It would be too complex to describe all the results. So based on these interesting results, a spin-off company was founded in the lab. It's called Wave Implant, and they are now working in the development of the medical device to hopefully have it available to surgeons in the future. Okay, so that's what for dental implant. I'm now going to describe another method that still aims at assessing implant stability, but that is dedicated to hip implants. So what is a hip implant? A hip implant is basically composed of two implants. The first one is what we call the femoral stem. You see it here. And the femoral stem is inserted in the femur, okay? The aim of the hip implant is to restore the functionality of the joint so that it can move, okay? The second part, the second implant is called the acetabular cup implant. It's put in the acetabulum, so right here, okay? And it's, you see it here, it's 5 centimeter diameter, okay? The implant, it's a hemispheric cup, 5 centimeter diameter. And basically, what the surgeon do is they remove the existing bone, and then they use a very big driller in order to drill a hole into the acetabulum, okay? That has a size that is slightly lower than the implant they will impact. And so the size is slightly lower, and so after that, they take this very long rod, they attach the rod here that you see here, they attach it to the implant, so it's something like this, and they take it like that, and they hammer the implant inside the bone. You can see on the internet, there are lots of videos of the surgery, and they hammer it really hard. I mean, it's a physical work, okay? And they ask everybody in the operating room to keep quiet because they are listening to the noise. And when the noise changes, gets kind of different, so it's really based on what they feel, they stop. And they say, okay, we are fine here. That's in place. Okay, Of course, they need to be careful with fracture risk. They also need to be careful with the stability because they don't want any micro movement, always the same problem. And they really relied on their proprioception. And I would like to advertise a nice talk that will be given in the same area later today in Westmont 1 by a group in KU Leuven in the same topic. Okay, so we said, okay, they use the noise, so we should measure this. And how can we measure? But the best way to measure is to use, probably all of you know the impact hammer is very widely used in order to measure what's going on during the impact. Okay, so that's what we did here. We just bought a piezoelectric force sensor and put it in front of the hammer and then gave the hammer to the surgeon and asked them to use it in order to impact the acetabular cup. Of course, there is a wire, we record the signal, and so let's see what we can get using this method. Okay, so in order to validate this, of course, we didn't do straight away to cadaveric analysis. We actually, since then, have done cadaveric analysis. You see it here. But initially, we didn't do that. We went to the butcher shop, asked them from bovine femurs, so you can have plenty of those for free. And then we asked the surgeon to make a hole just like what they would do in the clinic. Hemispheric hole, the size slightly lower than the implant. And then we asked them to use the impact hammer. You see, very simple impact hammer. And then after that, when it's in place, we record the signal. And then we just pull out the implant and measure the force. The force is an indicator of the stability. Let's see what we can get using this very simple experimental approach. We asked the surgeon to do different size of the hole. So in this case, the hole was too small. The hole was larger, at a larger diameter. Here is optimal, and then the hole was too big. So in this case, the implant just cannot go into the hole, so it's not stable, but we know. Okay? And in this case, the hole is too big so that it doesn't stay in place, so it's not stable either. And so when we use this simple configuration, measure the tangential stability, you see that we have a maximum for the optimal configuration here. And here, again, it's not stable because the hole is too small, and here the hole is too big. Okay, so you have a maximum. Very simple, nothing related to acoustics. But what is related to acoustic is the signal that you see here. That's the signal, what you get when you impact the hammer when the surgeon decided that it's stable. You have a first peak, and then you have secondary peak after that. These are reproducible measurements. We hit not too hard in order not to modify the implant, and we get pretty much a good agreement. And what we get here is that you see that the first peak is pretty much related to the energy of impaction. No, not really a lot of information here, but the information is in the secondary peak. And the secondary peak basically is of lower amplitude and arrives later when the implant is not stable. And this is logical because when the implant is not stable, it means it's less rigid, you have a lower resonance frequency, and so you have the secondary peak arrives later, and also with a lower amplitude. And that's what you get in terms of the indicator. The indicator is given by the amplitude, the integral of the signal in this time window, okay, that we determine in order to capture this signal right here. And so you have a maximum of this indicator because you always need an indicator, very simple for the surgeon, okay? And you have a maximum when the implant is more stable. But that's, of course, for one sample. We need to do a lot of samples using the same time window, the same way of measuring the indicator. And that's what you get for 20 samples. When you pull all results together, you see here the tangential stability, and here the indicator, and you see that you get a pretty good correlation between the stability on one side and the indicator on the other side. So it means that there is information on the implant stability that you can retrieve in a non-destructive manner using a simple impact hammer. Very briefly, we did also finite element analysis using 2D axisymmetric model. It was done using ANSYS. Large displacement, friction at the bone implant interface was considered using Coulomb's law, and linear isotropic elastic material were considered. And basically, so we have a mass drop, okay, very simple, and then you record what's going on between the hammer and the ancillary, the rod here. That's the variation of the hammer, the solid line is the variation of the position of the hammer as a function of time. You see there are rebounds, okay? So that's very simple, rebounds of the hammer. And you see that the dashed line here is the top of the ancillary. So it gradually goes down, okay, until a certain position where it's stable, okay? So that's the simulation, and you see how it goes in terms of image. The contact is pretty much here, and that's also logical with what the surgeons say, because they say that initially the implants hold in what they call the equatorial rim in this region. So that's not a surprise for the surgeons. Just to give you an idea of the signal that we get, we actually get this second peak, quite different because we did not consider viscoelastic properties, but pretty much the same trend in terms of the secondary peak. And we could also determine on a time window the impact momentum, so the indicator that was pretty much correlated on the contact area. And the frequency of this secondary peak was also correlated to the contact area. This is not a surprise, again, because when you have more contact between bone and the implant, you have a higher rigidity, a higher resonance frequency, so that's completely logical. Okay, I would like to just finish my presentation by drawing some perspective on the work to be carried out in the future. For sure, there is a lot of things remaining and needing to be done in order to understand the acoustical behavior of this interface, because we are really at the beginning of trying to understand what's going on, and there are lots of things to be done. Eventually, we'd like to solve the inverse problem. This is not done yet. Maybe using artificial intelligence, and Montreal is really in the center of this right now. So that would probably be a good approach, and also that we are counting on WaveImplant to do so, bring to the market medical device, and there is a demand for the surgeon. They would like to help to have some help in this direction using a translational approach. I would like to finish by thanking the funding agency, and of course all the group in Paris, all Giuseppe Rossi, Vuyu Nguyen, Salanelli, and all the PhD students, postdoc, and master students, without whom nothing would have been possible. And thank you very much for your attention.
Thank you very much for a nice presentation. I have a question about a dental implant. What I understand from your presentation is that you must not load the dental implant too early because it's not stable yet. Yep. On the other hand, you must also not wait too long because you are missing the stimulation effects from loading the implant.
Yeah.
I was wondering a little bit, does that vary very much from patient to patient, or is that did you investigate that maybe, because that could be an argument to do research on this? Can you comment on that?
Yes, it varies a lot from patient to patient based on the bone quality, but also from surgeon to surgeon and from implant manufacturer to implant manufacturer. The dilemma that is, as you mentioned, the surgeon need to make compromises. And the surgeon and the patient, they want to load it very quick.
Yeah, okay, that is one thing, but the quality of the result is maybe the most important one.
Yes.
To use the optimal waiting time.
Yes, and it's really a question optimal. in the time of surgery, in this time, if they see a very stable implant, they could say, okay, I'm going to try to reduce the time before loading. Even maybe try immediate loading. If it's not stable, they can say, okay, I'm going to wait more. But in the second time, they can also test. When they are about to put the prosthesis, the fake teeth, they can recheck. And based on the comparison with the initial results, they can say, okay, I'm going to load it now, or I can wait and ask the patient to come back.
You tested your approach, your ultrasonic approach, not yet on humans, did you?
No. It's well, the surgeon would like to do it, but you need to respect a lot of standards. We didn't electrocute any rabbits, but we don't want to take the chance on patients. So it's not us. Wave Implants, the company, is now working on all the certification.
It's not a dangerous thing, is it?
No, it's not dangerous, but you have standards. And I mean, if anything happens, you have patients. So you need to have I mean, it's not so complex. It's, as you said, ultrasound is even used to stimulate osseointegration. So it's not dangerous, but you still have electric signal, so no risk.
I will get an implant in about 2 weeks. I volunteer. I'll come to Paris.
Okay, you're welcome.
Older patients have some bone loss. Is this a problem for implants?
If the patient has bone loss?
Yes, older patients have severe bone loss sometimes. So what happens with the implant?
Yeah, there are different strategies that the surgeon can use. One of them is to use bone substitute material. They can use bone substitute material. We actually have tested this in vitro using one of it's a tricalcium cement. You have other strategies that you can use, okay? And they can put in, use biomaterial, bone substitute, wait until it consolidates, and then put the dental implant. We have tested it on in vitro on the tricalcium cement, and we imposed fatigue loading to the implant, and we showed that we could see a variation of the ultrasonic indicator as a function of the fatigue loading time. And that's another argument that we could use. But you're definitely right. There are different strategies, and and it's also very much surgeon dependent. That's amazing how surgeon dependent it is.
I understand as humans we're very close to pigs, so you can use a pig valve, and even I understand surgeons are thinking of using a pig kidney for a human. So can you use any pig bone at all? Would it be rejected?
There are several animal models that are widely accepted for implants. And the two animal models is rabbits and dogs. We do not like to work with dogs. We work with rabbits. But basically, we are working at mechanical properties. So, of course, mechanical properties of rabbit bone and of human bone are different, but it's not so different. So we're not looking really at a biological behavior. We're looking at a mechanical behavior. So bone properties may vary, but what we are looking at is the amount of bone, the quality of bone around the implant. So it's not like if you're using kidney, where a kidney is really different from one species to another one. Here you're just looking at bone. So you're right that the animal is important. So let's see what's happened when we test it in patients.
So you use the force signal in the hip implant case. Could you use just a sound signal?
There are some papers on that. some group. I think maybe in Leuven, I'm not sure, but I saw some Japanese group also. They tested it. For us, it was quite difficult because it really depends on where you put the microphone, how you put the microphone, how they impact it. We tried without success. The thing is that when you measure the force, you are just in situ. I mean, you are just right where it happens. When you put a microphone, of course, in the operating room, the microphone has to be quite far because you cannot, I mean, the access is very complicated, it's tricky. So you cannot have a microphone right at the implant, right? And so you are losing a lot of information. But yeah, there have been some group who did it. Yeah.
Thank you.
You say that you in the model and probably in slide 45 that you use homogeneous material for simulation.
Yeah.
Have you in mind to simulate orthotropic material, because bones are not inhomogeneous but orthotropic in some way?
Definitely. No, they're highly anisotropic. Yeah.
Okay. Because that method you use is very useful, for example, for indentation modulus to evaluate, is typical from indentation modulus where you test metals and something like that. But they are homogeneous and it works well. You have in mind some method to represent the orthotropic behavior of the material?
Yeah, that's a very good question. We actually, I didn't show that, but we did it for, in this case. We did it in another study. We consider an anisotropic behavior based on asymptotic homogenization. So we did, we determined the microstructure of bone sample, did asymptotic homogenization in order to derive the homogeneous anisotropic material properties, and then input it in this model. That's for the acetabular cup. And for the dental implant, you are right, but we should also consider the actual microstructure and viscoelastic losses, they're very important. But you are right, I mean, I said we are at the beginning, there is much work to be done, and that's a very good.
It's clear, it's clear. I know that it's very, very difficult.
You are right.
Just a curiosity, soft material you talked about, it was like hydrogels?
Yeah, we consider liquid because the shear wave velocity is between 1 to 10 meter per second. So in our case, we consider liquid, but we tried to consider soft solid. It didn't change much because the shear wave velocity is so low that it's really... And also you have a lot of attenuation of the shear wave in soft tissue. So.
It's more or less like water, so you have very few...
Yeah, we tried to vary this, didn't change, so water was fine. So, but that's yeah, that's maybe interesting also.
Thank you very much. Thank you very much.
Well, I think we are running out of time, so thank you for attending this conference, this last one, and thank you again, Guillaume.
Thank you very much.
Naturalmente amarsi e poi lasciarsi e andare a fare il check-in. Adoro partire, amo le hostess, amo il duty free check-in. Mi piace guardare la mia borsa, la